I would like to thank the organizers for setting up this conference and the program, and also the weather, so that you'd prefer to be here rather than going surfing on the beach. So thanks for the weather as well, which is somehow related to the things I will tell you today a little bit. Okay, so I'm from Bar-Ilan University, which is in the suburbs of Tel Aviv. And as Ilya has inputted, we have today more, in this audience, more people from Bar-Ilan than from Caltech. So I warmly invite you to come and visit us, hopefully when the situation will be a little bit more quieter. We have a nice campus, you know, close to Tel Aviv. So I'm a theorist, and my group deals with the dynamics of many-body quantum systems. And during the past few years, I've been working with these quantum computers, and I had the opportunity to collaborate with some of the manufacturers of the quantum computers, trying to use them and see what comes out of them. And of course, I would like to acknowledge my collaborators. So I would like to start with a bold sentence, which is that quantum computers exist, and one can use them. And here you see actually a partial list of companies that produce quantum computers, and most of them, they would allow you to connect to them with the cloud. And as you can see, they exist in many different countries. So this is the line I added with some startups, Israeli startups. And they also use different technologies, right, platforms. So you have superconducting quantum computers, silicons, NV centers, trapped ions, I mean, many different ways of building a quantum computers, which also. There's a question? Yeah. Well, let's. Can you? I didn't hear the question.
Can you comment on psi-quantum, because I'm curious, relevant to the topic?
So I know I have never used those quantum computers, so I really don't know. However, I can tell you that two of my former PhD students now work in Quantum Source, which is a startup that basically is building some building blocks that would be useful for psi-quantum. So I really hope that they will succeed. But I don't have any direct experience with that. Okay, the question that I think everyone is asking is, okay, what are these quantum computers good for? There are all sorts of questions, and the question I would like to focus on today is about quantum simulations. So there have been many different experiments, and I think the two that are most famous, mostly because they did a good job in PR, and also they are nice. Okay, they are also nice. Oh, this is recorded. Okay, anyway. It's two very nice experiments, very impressive, by Google, in which they realized new phases of matter, like a time crystal and the quantum wormhole that will destroy our entire universe. But actually, I would like to draw your attention to two works that were published, posted online just 3 days ago, in which they realized a group from Harvard and a group from Munich, using the Google platforms. They realized a two-dimensional topologically ordered phase with fractionalized excitations. So, and using Floquet-Hamiltonian. So, I mean, these are very interesting works that you can look online. And actually, you know, they resonate with topics that we've heard here. So, Floquet, topological order, fractional excitations, etc. So, you can check them online. Now, what my group have been focusing on is what I would call a poor man's quantum simulations on the cloud. And poor man's really means that we don't have a lot of budget, so we can't really run a lot. And then, but there is also poor man's also because these quantum computers that exist today, they have very limited capabilities. And so this is a flash of our recent works on the topics. And what is nice about these works is that, first of all, we did them. And second, in each of these works, there is at least one graph that comes out of a simulation on a real quantum computer on the cloud. And in all these works, we were limited to up to 6 qubits, which is basically the quantum volume of current generation, or at least, until very recent state-of-the-art quantum computers. Which, so in other words, what we were trying to do is to write a poem with 6 words of 6 letters. Okay, and still you can write all sorts of poems, and there always was some theoretical question that was behind, or maybe the quantum computer was a motivation for this work. So I think there is a very nice, although you could simulate all those quantum computers, all those simulation calculations on a classical computer. I think the motivation, the point of view is a little bit different, and this gives rise to new questions that maybe you wouldn't have asked if you didn't have the quantum computer in mind. Okay, so for today, I would like to talk about harnessing quantum optical theory techniques in simulating solid-state materials. So it's very on topic with very in line with the topic of this conference. And I chose two of our recent works. Yeah, I hope you will like them. So this is what I would like to tell you today. Two recent works. The first work is related to an experiment, or this quantum simulation by IBM, a recent simulation, which is called the quantum utility experiment. So what is the idea? So the idea is to simulate the dynamics of the transverse field Ising model. I'm sure you all know this model. It has a coupling and it has a magnetic field. And what they did, they realized this experiment on a quantum computer with 127 qubits. So that it was quite impressive what they were able to achieve. I will show you the results in a moment, but there is one important caveat when studying the dynamics of an Hamiltonian like this one, is that it's quite easy to realize a gate that acts as a magnetic field. So that's just a rotation around the x-axis, very simple, like this basically Rabi rotation, and a coupling, right? This would be your gate, your entangling gate. So these two ingredients, you know how to realize them, but you cannot realize them at the same time. So how you solve this problem is using what is known as the Trotter expansion, which means that you basically first apply, let's say, the coupling, and then the magnetic field, and then the coupling, and then the magnetic field. So you split your Hamiltonian in small time steps, and you repeat one after the other. In reality, even the ZZ coupling, you cannot apply all of them at the same time, so you apply basically the red, then the blue, then the green, and then again, then the magnetic field, then red, blue, green, etc. So what is interesting about this realization is, first of all, that's the way it works, but also it's interesting because it is really a periodically driven system, right? You are periodically exciting your system, and there are some experiments, including, for example, this time crystal that I mentioned before, or also Floquet topological phases like the one that we realized, and also others on a quantum computer, which really rely on the fact that the dynamics is really a periodically driven dynamics. So I would say for these, there is always a question of what is natural to perform in a quantum computer, and this type of dynamics, it's this periodic drive, this kicked periodic drive is very natural for those computers. But I would like to put that aside for the moment, and I would like to focus just on the dynamics of this model without taking into account the periodical drive. So in this experiment by IBM, what they showed were two simulations, one with 5 time steps and one with 25 time steps. So a time step means a repetition of all these protocols, right? Magnetic field, Z, magnetic field, Z, so they did it 5 times or 20 times. And what you see here are the results. So this is the average magnetization. Okay, the magnetization is just, you think that the 0 state is 0, and then so the down state is 0, the up state would be 1. Or maybe the other way around. Well, certainly. So 1 is basically 0, 0, 0. So you initialize, in a quantum computer, you always start with the 0, 0 state. So at the beginning, all the spins point in the x direction, in the z direction, and if you don't apply the magnetic field, so here basically you don't do nothing, right? Because the qubits are all in the 0, and you apply the z gates, but you don't rotate them, so they stay there. And while as a function of magnetic field, okay, there is some shape that comes out. So what do we see here is an exact simulation. So because the time evolution is not too large, you can simulate. I mean, it doesn't, each of these gates creates some entanglement. But if you do only 5 steps, the amount of entanglement you create is not too much, and then you can simulate these dynamics even although there are 127 qubits. What you see here in green is the experiment, and you see it sort of follows the exact result, but it's not on top. However, and that's the impressive part of the paper, is that they used something called as noise mitigation. In particular, a special technique that is known as zero noise extrapolation technique that basically brings these green dots to the blue dots. So how does that work? So what you do, but it's a mathematical, it's very, okay, sure. It's quite intriguing. It's quite an intriguing technique. And the way that it works is that, first of all, you characterize your noise very well. So you characterize the noise by using Pauli matrices, whatever. So you know exactly which noise you have. And then what you do, you enhance it. So you mimic what would be the effect of having more noise. And then you draw a line in which you have your state, the normal simulation, and then this normal simulation plus noise, plus 2 noise, 3 noise, and then you actually extrapolate to -1. So what would happen if you didn't have any noise at all? And you do that for each point. So each of these blue dots is really obtained by performing all those experiments and extrapolating them back to zero noise. It's called zero noise extrapolation. Honestly, I was very surprised by how well it works. Okay, the caveat, there is always no free lunch except at the KITP, but the caveat is that you need to do a lot of experiments, right? So you need to characterize this noise very well, and you also need to repeat the experiment with the usual experiment and the usual experiment with noise. So you need to really do many experiments. Yes?
Is there a reason why this works? Does it depend on the kind of noise? Is it like dependent on the particular model of noise that I add to increase the noise?
Yes. So the type of noise that you use is basically a Lindblad master equation or these Krauss operators, and you expand it using Pauli matrices. So you basically take into account any type of local noise. So you assume that the noise is only local, and you try to, there is always, there is some assumption behind it, but it just works. That was the surprise. I mean, how well it works. Yes?
Okay. So they actually know all their noise channels, right?
Exactly.
So
that's the idea.
Let's say like we remove one of those noise channels, they cannot actually get this well, right?
I don't know. Yes. So we should ask them. So yes. In principle, okay. This is the average magnetization. So now you performed only 5 steps. So you don't make interactions between all 2 qubits to all qubits. So if you do take out the noise in 1 qubit, you'll probably get a wrong result for 1 qubit. But here I average over 127 qubits. So presumably is not that destructive is if you just take out one of those channels of noise. Yeah. Okay. Yeah. One more question.
So just to understand, so in a sense, the knowledge that I have is the knowledge. I mean, I extract the knowledge out of the noisy system, and then what sort of disturbs me a bit is then, isn't that sort of going into a classical computer? I mean, in the way, because I'm sort of, whatever we extract is obtained from the noisy system, and just characterizing it as function noisy. So how do you get the real information out of it, which you could not get from a classical computer?
No, so what you do, you run those experiments on the quantum computer with additional gates that mimic the noise. So how do you enhance the noise? You do more experiments on the quantum computer that take into account the more noise. Now, the information that you have is which probability you will use. So how much of each noise you will add. But that's what you do. So you have the quantum simulation, the usual one, and the quantum simulation with additional noise, with additional gates that mimic the noise. So it's really coming out of the hardware that you cannot, I mean, if you can simulate on a classical computer, fine, but that's not straightforward, okay? Exactly. This is just if I ran it, okay? If I ran it, I would get the green dots. If I paid, if I had money. Okay, so now, then in the paper, they also had the same, but with 20 time steps. So 20 time steps, it means you have much more entanglement because you are, evolving for longer times, and then you don't have any exact simulation. And they claim that, you see, they can do the mitigation. We know that at least this blue point is okay, and presumably these other blue points are also fine. So that was the idea of a utility, that you can simulate a system that cannot be simulated classically. And that was true for 2 weeks, because after 2 weeks, there were 3 papers in which they simulated this using advanced classical. So you cannot simulate it using the wave vector simulation, but you can do it using more advanced techniques, like in particular this work by Dries, in which they used tensor networks in an appropriate way, and you see that these they reproduce very well the experimental results. So the experimental result works very nice. The only problem was that, yes, you do have a way to simulate these using tensor networks. And then Google went one step further. Basically, they use the same ideas, just Google-like. So, and they say this allows us to produce the results of reference 7, which is the IBM, in no less than 1 second per data point using 1 GPU. So, they did it very, very carefully. And there is also another paper, very nice, in which they use an expansion. So it turns out that for the parameters that were used in this quantum computer, in this quantum simulation, many of the gates are actually Clifford gates, so they are easy to simulate, and then there is a way to expand non-Clifford into Clifford, and the Clifford are classically very simple. So anyway, there was another paper also, in the same few days that reproduced these results. So I think it's interesting that, the experiment, although it was not useful, but it was useful to create new science, new research, understand better, to give motivation to theorists to do some work and develop new ideas. So in that sense, it was very useful. So the question I asked myself is that, is there a simple description for this dynamic? So I was sort of surprised by the fact that this curve looks very simple. And I asked myself, can I have a simple description of it? Yes?
Can I ask a nice question? So why should I add noise by hand in the experiment? Like there will be inherent noise in the experiment, I will add by hand in my theory. Like why should I add noise in hand? Like
you added the noise so that you can extrapolate zero noise. Let's say you have 100% noise, then you simulate 120%, 150%, 200%, and then you get a line, and you can extrapolate to 0%.
Okay, understood.
Okay, basically, it's like when you have a student, and he comes up with some simulation, you send the paper, and then he says, oh, I want to see the finite size scaling. So the student comes, works for 2 weeks, comes back, says, I cannot. I mean, we don't have enough power. So they say, okay, you know what? Just look at smaller system sizes, right? If you can look at, so that's exactly the same idea. Okay, well, great. So my question is there a simple description? And so I tried something. So the idea was to first try a mean field analysis. To try the mean field analysis. So the mean field, if you don't know what the mean field, how do you do the mean field for spins, then I really encourage you to look at this paper, this book by us. At least that's where I learned about this, and we are very sad. We were very sad here to learn that Asa unfortunately passed away just a few days ago, and he was really very motivating person and one of the pillars of the quantum community in Israel, and we really miss him a lot. So anyway, assuming that I understood what the book is talking about, so what is mean field? So mean field means that instead of having an operator that is a product of 2 operators, right, so Zi, Zj, you substitute Zi with the average value, okay? So that's the idea of mean field, and then what you can do, you can compute the average value in a self-consistent way. So at each step, what is nice here is that in this dynamics, really a discrete dynamics. So you can really do it step by step. So what you do, you compute the average Z, then do what is actually a single qubit rotation. So you see, after I did the mean field, what I obtained, this is just a single qubit rotation around the Z-axis by a value that is computed classically. So what is nice about this approach is that it translates a many-body problem into a single qubit, right? Into just a rotation of a single qubit. So that's just the product of 2x2 matrices. It's almost analytical, I would say. The problem with this is that it doesn't work. So you see this green line, apologize for the colors. It sort of works at the beginning, so you feel like I'm probably onto something, right? That was the feeling. I'm onto something, but it still doesn't work. So yes, okay. one can understand where these oscillations come from. So what was the new thing that we tried to introduce? So the idea was the following. So that you have mean field, and then you have also something that is not captured by the mean field. But this thing that is not captured by the mean field is what? Is essentially like a fluctuating magnetic field, right? It's like a random rotation. So you have an average rotation, which is captured by the mean field, but you also have some random fluctuations of the magnetic field. And this is where quantum optics comes to help, because you know that a random rotation of the magnetic field is basically dephasing, right? That's the T2, the famous T2, pure dephasing. This would be a model for pure dephasing. And in quantum optics, we know how to introduce them using these master equations or these Krauss operators. So there is a very simple way to introduce dephasing into the dynamics of a qubit. This is just really standard, I would say, or standard textbook quantum optics. And that's what, okay, so then what you do, what is nice is that you can compute these fluctuations in a self-consistent way. So not only you compute what is the average value, but you also compute what are the fluctuations in a self-consistent manner. So what this approach gives you is, again, a model with a single qubit, but it's not anymore a unitary model, it's an open quantum system, okay? If you want, it's a driven dissipative quantum system, right? It's a system that has dephasing, and it has a drive, but it's a single qubit. It's very easy to solve, and that works much better, okay? So this is this orange line. I think it follows the curve very well. Of course, it's not a numerical exact method. One could extend it to a numerical exact method if instead of having a Markovian buff, you would take into account non-Markovian approximation, and that would really give rise to essentially a dynamic mean field theory. So if you want what we did, I would say it's a poor man's dynamic mean field theory that it has only Markovian approximation, and I think that it sort of captured the physics. So I was sort of satisfied by my theoretical, quest to try and understand this dynamics, why this shape looks so simple. And the idea is that what you are having here is essentially just the dynamics of a single qubit plus some dephasing that comes out of the neighboring ones. Yes?
So this is converging to the experiment after you do the noise mitigation on the experimental data, or?
Yes. When I wrote here experiment, I mean experiment after noise mitigation. Yes. Yeah.
Okay.
You say, okay, if I see your suggestion, you say, maybe what you could do, you could also add other type of noise and reproduce the system without, prior to the noise mitigation. Probably one could do that. I mean, just if you probably add some qubit decay, right? This is just dephasing. So T2, probably by adding T1, what you would probably observe is that this value would go down. I haven't done it, but it's a nice idea, yes. Yes, Hanan.
Is there any hint that we're not fully there yet by the fact that that Z goes to negative values?
The Z can go to the negative values. I mean, it actually goes between -1 and 1.
Yes. No.
So,
I know it's physical. I'm just saying, but like.
I don't think that there is a way a priori to know that it could not be negative. I mean, I don't know. I don't know. Okay, I don't have a good. We'll have time to discuss. Yeah.
This might be related. So how does the time dynamics compare with the Markovian approximation? Like you also.
So can you
like if
elaborate?
if you compute this in time, like because if the dynamics is Markovian, then like they would have very specific pattern, like time, I guess.
Yes. So this is in time. I mean, this is after 5 time steps. And then maybe you ask, okay, what happens after 25 time steps? Oh, and that was the referee's question, so I haven't had time to answer. Yeah, I think it's well, I don't know.
This is like T equals to 5J.
This is T equals to 5. This is after 5 periods of this periodic drive. And actually, if you see those oscillations here are related to basically, if you have a mean field, then you rotate 5 times. So these are these 5 oscillations. So after 20 times, you would see 20 oscillations. But the point is that you have dephasing. So the idea is that what's going on here is that the other qubits, eventually it's a simple story, right? The other qubits are acting on your qubit, on your mean field qubit, as a dephasing channel. That's the idea. The only point I would like to make is that sometimes you can capture the dynamics or the key ingredients of the dynamic by just using a Markovian buff. Of course, if you want the true dynamics, you'd better take into account non-Markovian effects as well.
So you said that by basically using colored noise, you would get almost exact, but at the same time, this is still a very low-dimensional network, right? If I remember, it looked like there are some sites which have only 2 neighbors, so would I expect this mean fieldish, even with fluctuation approach, to be good?
Yeah, well, I mean, you see, you can, in principle, you can do, in principle, what I'm saying is, you can always integrate out whatever your system is. And so if you describe that correctly, then yes, I don't think there is any, I mean, I think you are saying, you say this is not, yeah, I would say the answer is yes. Although it's a low-dimensional system, if you take into account the correlations correctly, I think one could do that because you are just integrating out the rest of the system.
Okay.
Yeah.
This noise, I mean, you take it global. You take this noise global, or this delta Z. I mean, I would have more the intuition that if there's some noise, then it's more local. Adding to this non-Markovian discussion, but that's a different point.
No. So it's very local, right? It's a very local noise. It acts on my qubit. I have one qubit, which is my mean field qubit. Yeah, right. And I have a dephasing, which comes because of that
but
qubit.
The delta Z acts the same on all J, or?
It acts, well, I actually have just one.
Okay.
You could, if you want, there is an extension, that's something I did, in which you take into account the mean field for each qubit individually, and then the delta J will be different for each qubit depending on the connectivity. Gives the same result. Not better, not worse. Last question, because I wanted to speak also about another topic.
Okay, I'll take one more.
But here, the mean field ansatz is a single site, basically, of the lattice, but the lattice has, to Martin's question, like 2 or 3 different inequivalent sites. If you just averaged over 3 different sites, these.
So I did that. I mean, I just did these 127 mean field theories and average over them, and the result is very similar to this one. It did not improve.
Oh, okay.
It's very similar. Okay, so the second project I wanted to tell you about is about some universal scaling and about some wave propagation. So that's the relation to what you have seen spoken here. Okay, so I have an historical background which tells you that people some time ago believed that the world was causal, which means that we can affect only the future but not the past. And then this was improved by Einstein, who said, well, not only you can improve the future, but actually you cannot improve anything that goes faster than the speed of light, right? There is no way to transfer information faster than the speed of light. So that defines for your causal light cone. That's true in general relativity. Now, if you take a material, because here it's a topic about materials, then you have quasi-particles, and quasi-particles propagate as wave. So in the same way that light has this light cone, there is a light cone for quasi-particles, whose velocity is not the velocity of light, speed of light, but it's the velocity of the quasi-particles. So of course it doesn't, so that's quite simple. And this argument, qualitative argument, was then made rigorous by what is known as the Lieb-Robinson bound. And the Lieb-Robinson bound tells you that independent on the presence of quasi-particles or not, there is always a light cone. And that light cone is determined by the properties of the Hamiltonian. And if you go outside of the light cone, there is an exponential suppression. So essentially, quantum fluctuations can cause the propagation of faster than the speed of sound velocity for that material, but very little. Okay, there is an exponential suppression of the information that you can transfer faster than the speed of sound. Nothing, of course, faster than the speed of light. But okay, these are. Okay, good. So that was sort of known. The question that I wanted to ask myself, that we ask ourselves, and again, this is a collaboration with my postdoc Mona Lisa and with Duncan O'Deal. So what happens inside the light cone? Okay, so let's do a simulation. Okay, so here I have space. So space are my spins. So my spins are, let's say, all 0. That would be mean. So all the spins are pointing down. Let's say you have one spin that is pointing up. So in terms of quantum computer, by the way, if you want to become a quantum information theorist, you just change the word spin into qubit, and you did it. Okay, so basically here you have a string of 0, 0, 0, 0, 1. That's your perturbation, 0, 0, 0. So there is a local perturbation in the middle, and then you try to see how that propagates in your device. And this is some numerical simulation. So you have in the x-axis the time, and you see that there is this light cone. Okay, so the light cone is indeed the speed of sound for this system. But what is remarkable are those oscillations. So what we wanted to study is what is the nature of these oscillations. So what you can do, you can take a cut. Okay, a cut for a fixed spin as a function of time. And what you will observe is that, okay, so let's say the light cone is here. So of course it depends where you cut. So if you cut after 10 spins, then you will have the light cone at, well, okay. In this case, the light cone is a 10. There is an exponential suppression. So that's the Liber-Robinson bound tells you that there is an exponential suppression on the left. And there are some oscillations on the right. And then you ask yourself, what is a function that is exponentially suppressed on the left and oscillating on the right, or you can also invert it. You know which function is it? Airy function, okay? That's an airy function. Airy function is, so it's minus airy function. Airy function is exponentially suppressed on the positive. Anyway, so it's an airy function, and indeed, that's, I guess, a demonstration, but if you want to see some actual calculation, in the weak coupling limit, for the Bose-Hubbard model, and for the spin model, you can really demonstrate that it's an airy function. And in fact, what Duncan explained in this paper is that the fact that it's an airy function relates to a more general concept, which is called catastrophe theory. So catastrophe theory is a theory that is aimed to describe a physical effect, which is called caustic. So caustic are those lines of increased reflection that you can see, for instance, if you look at a pool, or probably even at the sea, right? If you look at the pool, you don't see random white dots. You see those sort of lines, right, of reflection of the light. And those lines are called caustics. And if you look at the oscillations around them, so there are also oscillations, these oscillations will be generically described by an airy function. Okay? So that's the generic result of the catastrophe theory for wave propagation. Okay? But the question that we wanted to ask is what happens if you add interactions? So if you do in the many-body quantum physics regime. My understanding was that I don't know what it is, but it's definitely not an airy function. Okay? That was my point of view. Well, just it's an interacting theory. It cannot be the same, right? Something must change. So if something must change, then what can we say? And I said, maybe what we should look at is a scaling law. So an airy function has this 1/3. There is 1/3 inside or 2/3. I mean, there is 1/3 that comes out of the airy function. It's just because an airy function is like an integral of e to the I, k to the third. Something that's sort of an airy function. So there is 1/3 that comes out of airy functions. And I said, maybe the airy function will be dead, but the scaling law will be the same. That was the ansatz. And so what we said is the following. So this is actual numerics. So we said the following. Take these two peaks. So this is the Liber-Robinson bound. Take these two peaks, okay, and divide them by renormalize them, right? You want a unitless number. So you take this delta t and divide it by the time, and then you look what happens when you move away from the propagation. So when you move along the light cone, you always see these oscillations, and you take this unitless number, and if it is an airy function, then this should go as j to the minus 2/3. So j is the distance from the perturbation, from the spin perturbation. So that was the answer. So this is it seems to work. I mean, in the numerics, what we did, we really did that. So we took these two peaks and then repeated for different distances from the center. 1 second, and then we fit it to a power law. And then we took the exponent. That's what we did. And indeed, what we found was that the exponent seemed to be constant close to these 2/3, at least for small interactions. When you add large interactions between the quasi-particles, these numbers sort of change. But we were sort of happy because at 1, you have a quantum phase transition. So then we claimed that this universal scaling is correct up to the quantum phase transition, and then the quasi-particles change. What we know for sure is that these oscillations it's a little bit, somehow has something to do with Friedel oscillations. So these are oscillations that come because of the quasi-particle nature of the model, and we know that the quantum phase transition, the quasi-particles change their nature, and then we try to relate these. I don't know, the referees were not completely convinced, but I think that was my opinion. So there is more work to do. I've been discussing a little bit with Sebastian whether this has anything to do with KPZ dynamics, but I'm presenting here some numerics. Okay, so I would like to conclude by saying that I've described here two recent projects of ours, one with my student Mo Roses, who recently graduated, where we described many-body dynamics using a single qubit master equation, and the second project with Mona Lisa and Jesse and Duncan, in which we studied, we tried to propose a universal scaling for the quasi-particle dynamics in relation to caustics. So, because there are no more questions, we actually have another, also it's, it's like on YouTube. This will be on YouTube, right? So on YouTube you have advertisements, and that's why I want to show you two advertisements. So advertisement number one is that there is a company, it's called Quantimize, and I'm one of the co-founder. And what we do, we try to find real-world application for noisy quantum computers. And in particular, we focus on these combinatorial optimization problems. So if you have a really important optimization problem that you're trying to solve, then come to us, we'll solve it for you very efficiently. We have a few POCs, and it really works very, very nice. And the second advertisement, which is very important to this audience, and actually you can ask Victor, which is one of the first 10 subscribers to smartarchive.org. It's a system that gives personalized suggestions of daily preprints, at least when my server is on. So today there were no. Victor, did you see that? It didn't work today. It just crashed. Yes, it crashed, and I'm abroad, so no connection, nothing.
Emanuele, how many subscribers do you have so far?
So Victor was 11.
He was one of the first 10 you just said. Now he's 11.
Sorry, no, the 10. You're right. No, Victor was 10, so you're welcome to be the 12.
Does one have an advantage if one is earlier, lower number compared to later?
Well, you make me happy. So
okay, I will be number 12.
I get an email every time someone subscribes. So, yes, okay, well, that's it. Okay, so thank you for your attention.
So, out of the 10 papers you get every day, how many of those are yours?
No, no, actually, I can tell you, this is actually an interesting question. So, first of all, I don't have that many papers, but in any way, my student actually submitted a paper 2 days ago. I didn't get it. No, really. It was that's the way it is. I don't know. It's very smart.
Thinking about your second topic, yes. Does the result change if you, instead of having spins, you would have boson, basically bosonic excitations?
Right. So the answer is no. At least. So there is there is a theory. Actually, I cited it here. Where they cited the Bose-Hubbard. So it's cited here, this work by Corinne, where they studied the Bose-Hubbard model, and they also recovered this Airy function in the weak coupling limit. Okay. Now, what happens in the strongly interacting regime, we don't know. I mean, whether this scaling is correct or not, it's unknown, just because it becomes very complicated to compute those things.
Thank you.
So I hope. The idea was, I hope that this universal scaling will be a way to sort of try to extend in a regime where we cannot calculate exactly.
And what if you add dissipation? I mean, because you're now, I assume, in the way you set up your model, this thing will just expand up to infinity. If you now put dissipation in your system, what happens?
Yeah, I don't know. I mean, this is for unitary dynamics. Presumably there is, I don't know, probably some broadening, but yeah, it can be, right, at some point so the light cone is ballistic expansion, and after that it becomes diffusive. right? So you go from a linear light cone to something more parabolic. So that would be my prediction. So these predictions refer to the light cones themselves. So I would say it's until some time scale before dissipation kicks in. That would be my guess. Yeah. Presumably, if it is diffusive, you would just get some uniform. You don't see, so you lose the visibility. That's also. As you I mean, when I spoke about these numerics and I said I'm not completely sure, first of all, that was the referee remarks, but also there is a question of visibility. So is it really that the exponent changes, or maybe I just don't see those oscillations anymore very well? So, and it's a little bit hard to, ambiguous to distinguish. So there are open questions here, even in terms of the numerics. I think Hanan had a question before. Okay, thanks.
John?
Thanks. Maybe I missed the Hamiltonian for this. It's transverse field Ising model with, or what was the Hamiltonian?
Yeah, it's the transverse field. It's the same Hamiltonian as before.
The interacting one?
It's the transverse field in 1D. So it's yeah. So yeah. Okay. Good. So it would be just the transverse field Ising model in 1D. The way we realized it, by the way, because we had in mind an implementation of a quantum computer, was doing a Trotter expansion. So it's actually the evolution in the Trotter expansion. However, because you are looking into the long-time dynamics, this Trotter expansion didn't seem to harm too much.
But it's solvable by like exactly solvable? Or?
Okay, so so you're right. So we also consider the effects of integrability breaking terms. So basically, an interaction that would look like basically a XX. If you had some small JXX term, that would be like an interaction between the fermions, so it's not anymore exactly solvable. And the exponent seems to be stable, at least to some extent, to non-integrability breaking. So I don't think I think it really has something to do with the low energy physics of these quasi-particles, rather than with the integrability of the model.
Any other questions? If not, let's thank Emanuele again.